Welcome back. So, again, it's my pleasure to introduce our second speaker, Olivier Benoist from École Normale Supérieure. And he will talk about smooth subvarieties of Jacobians. Please.
Thank you very much. Thank you for the invitation. I'm very happy to speak in this seminar. And I'm going to talk about a joint work with Olivier Debar about smooth subvarieties of Jacobians. So in all the talk, I will consider over the complex numbers, a smooth projective variety of some dimension n. And I will always write n is equal to c plus d. Okay. Where c will be codimension of cycles and d dimension of cycles. Because my goal will be to study subvarieties of x, y, so of dimension d, or of codimension c. And with such a subvariety, one can associate a cohomology class, the class of y, which lives in the singular cohomology of x with integral coefficients in degree 2c. And these classes are called algebraic, and we denote by H2C alg of x inside the cohomology of x. The subgroup of algebraic classes, which is exactly the subgroup generated by such classes. And of course, it's an important invariant of smooth projective varieties. It controls the geometry of the variety X. The point of this talk is that the subvariety Y may a priori be singular. And it's a natural question whether algebraic classes are generated by classes of non-singular subvarieties, of smooth subvarieties. And this is a question that goes back to Borel and Heffliger in 1961. Is this subgroup generated by classes of smooth subvarieties? So in some sense, when studying algebraic cycles, can one restrict to smooth subvarieties? And in some cases, yes. So let me list the cases where the answer is positive. So, okay, if we look at 0 cycles, they're points, they're smooth, there is no difficulty. And it's also very easy to obtain a positive answer for cycles of codimension 1. So for cycles of codimension 1, they're divisors, so they're combinations of very ample divisors, and by Bertini, very ample divisors are represented by smooth subvarieties. So those are the easy cases. And there are also non-trivial positive results. So the first one is about concerned low dimensional cycles. So cycles of dimension at most 3. And in addition, below half the dimension of the ambient variety. So if the dimension of the cycle is strictly smaller than the codimension. And so this is a result due to Hironaka in 1968. And the other result that is known are 2 exceptional cases. So for codimension 2 cycles in ambient varieties of dimension 4 or 5. And this is a result of Kleiman. And I have written here all the positive results that are known about these questions. And in general, the answer is negative. So let me write no in general. And let me list the negative results that are known. So the first negative result for codimension 2 cycles on varieties of dimension at least 9 were constructed by Hartshorne, Rees, and Thomas in 1974. And really their method, their argument should give counterexamples, should work for any value of the codimension, at least 2, as soon as the dimension of the ambient variety is big enough. So in the case of codimension 2 cycles, examples on lower dimensional varieties were constructed by Debar. So for codimension 2 cycles, now on varieties of dimension at least 7. And the last counterexample that I want to mention, okay, so works for only for some values of the codimension. So let me write if alpha of C plus 1 is at least 3. So the definition here is that alpha of an integer m is the number of ones in the binary expansion of m. So it's an arithmetic condition on here the codimension of the cycles. And so for those values of the codimension that satisfy this arithmetic condition, there are counterexamples as soon as the dimension of the ambient variety is at least twice the codimension. So this is a result by myself. And so the reason why this result is interesting is that for these values of the codimension, it gives counterexamples of comparatively low dimension. Okay. And in this talk, what I will do is develop the counterexample constructed by Debar. And so let me write what the counterexample of Debar is. So Debar considers a variety X that is the Jacobian of a curve for a very general curve of fixed genus. So C, very general of genus. So say genus n, so that the Jacobian has dimension n. Now there is a preferred cohomology class in this situation, that is the class of the theta divisor that lives in the second cohomology group of X with integral coefficients. So it's the class of the theta divisor. And to this class are associated the so-called minimal cohomology classes. So this is the of codimension C. And on Jacobians, this class is always an algebraic class. So it is the class of well, the image of the symmetric product of the curve by the Abel-Jacobi map. So it is the class of a subvariety. It is an algebraic cohomology class. But the image of the symmetric power of the curve in the Jacobian is typically very singular subvariety. So there is no reason why this algebraic cohomology class should be the class of a smooth subvariety or a combination of classes of smooth subvarieties. And what Debar does is that he shows that indeed, in general, it is not. So what Debar does is he shows that this minimal cohomology class is not a combination of classes of smooth subvarieties. For codimension, for C equals 2, if the Jacobian has I enough dimension. So in the range of his theorem. And the goal today is to extend this result to many other values, well, of the codimension, of the dimension of the Jacobian. So I will state right now our main theorem.
Sorry, before you continue, could you say a bit about the varieties that are considered in other counterexamples?
Oh, yes, very good question. So for Archon and Thomas, their example are Grassmannians. So Debar, I told you, are Jacobians, so abelian varieties. And in my examples here, the variety is a quotient of an abelian variety by a fixed 0.3 action of a finite group. So it's a quotient of abelian variety.
Non-trivial.
As you see, the answer is negative even for varieties with very well-behaved geometry, like Grassmannians.
Okay, thank you.
Are there other questions? Okay. So the main theorem, so is due to myself and Olivier Debar. So you take C, a very general curve of genus N. You define x theta to be the Jacobian of the curve, polarized by the theta divisor. Now we'll make an hypothesis on the codimension, an arithmetic hypothesis on the codimension, that is alpha of C plus alpha of C is strictly bigger than alpha of C. So it is a very weird condition. Recall that alpha, I've just given the definition, we're just recalling it. Alpha of M is the number of ones in binary expansion of N. So for those values of the codimension, and if the dimension of the abelian variety of the Jacobian is big enough, so bigger than 4c minus 2, then the minimal cohomology class, and more generally, the multiples of the minimal cohomology class with odd coefficients. So is algebraic. So I've already explained why it is an algebraic cycle. but is not a combination of classes of smooth subvarieties. Okay. So let me make a couple of remarks. The first is that, okay, this weird condition on the codimension, okay, holds for many values of C. So 2, 4, 5, 8, 9, etc. And for codimension 3 cycles, we know nothing. So we do not know if there exist Jacobians such that the minimal cohomology class is not a Z combination of classes of smooth subvarieties. So really, our method is restricted to those values of C.
So are there infinitely many C satisfying this condition?
Yes, yes, absolutely, absolutely. If you write them down, like roughly half of the C's. And yeah. And an interesting corollary of the theorem is the case where C is equal to 2 and N is equal to 6. In this case, the theorem applies and shows that there exists over the complex number a smooth projective variety of dimension 6 such that the degree 4 cohomology group contains algebraic classes that are not combination of smooth subvarieties. So this group is not generated by classes of smooth subvarieties. And the reason why this corollary is interesting is that, well, in view of the positive results that I have quoted above due to Hironaka and Kleiman, 6 really is the lowest possible dimension where there can be a counterexample. The smallest possible dimension of a counterexample. So the corollary is optimal, gives an example that is optimal in the sense that it is of minimal dimension. Okay. Let me now say one word about the proof, the tools used by the bar. So the bar's argument is based on 2 main tools. So the SER construction that relates codimension 2 cycles to rank 2 vector bundles. And it is a tool that is absolutely specific to codimension 2 cycles. The second tool is the Hirzebruch-Riemann-Roch theorem. And the difficulty to extend this method is that it leads to computations that are intractable when you look at higher codimensional cycles. And so we need to devise an argument that is different from the argument of the bar. And we need to replace these two tools, the circumstruction and the Hirzebruch-Riemann-Roch theorem, by something else. And in fact, we replace both by arguments that are based on complex cobordism. So by a systematic use. And what I want to do now in the rest of the talk is to explain the proof of our main theorem and doing so to advertise the use of complex cobordism for this kind of for the study of algebraic cycles. So what do we want to do? So we fix inside X. So recall that in our main theorem, X is a very general Jacobian. And we fix inside of X a smooth subvariety of codimension C. And our goal, and keep that in mind, is to find restriction on the cohomology class of Y. This will show that cohomology classes of smooth subvariety cannot be arbitrary. In particular, you cannot obtain odd multiples of the minimal class. So this is the goal. This is what we need to do for the proof. And as I told you, I will use complex cobordism. So let me first define it. So complex cobordism is really a homology or cohomology theory, if you want, that looks a bit like singular homology with integral coefficients, except that it is based not on sums of simplices, but on complex manifolds somehow. So it is the kth complex cobordism group of a topological space X is generated by continuous maps from M to X, where M is a compact complex manifold. So, except it's not exactly complex, it's stably almost complex manifold of dimension K. But you should think of it as a complex manifold, really. And what stably almost complex really means is that you put a complex structure, so on the tangent bundle of M. So that would be an almost complex structure. And here I will put a complex structure not on the tangent bundle itself, but on the stable tangent bundle that is on the tangent bundle to which I add a very large copy of the trivial bundle. I stabilize it by adding a very large trivial bundle. So those are somehow the cycles, the chains on which complex cobordism is based. And of course, I need to quotient by a relation, by boundaries, like in usual singular homology. And the relation I impose is the cobordism relation. So two such maps, F and F prime, are deemed equivalent, cobordant, if we have the following picture. So this is X. I have the map F here from M. I have another such map F prime for M prime. And they're equivalent if you can find a compact manifold with boundary, whose boundary is the union of M and M prime, and the map big F that extends little f and little f prime, compatibly with stably almost complex structures. Okay. And what I claim is that so defined, these complex cobordism groups, they have all the properties of singular homology. Like there is Mayer-Vietoris, excision, I don't know, long exact sequences, compatibility with suspension, I don't know, all the formal properties of singular homology are still valid for complex cobordism, except for one, so that I will state as a theorem of Milnor. So if you compute the complex cobordism ring of the point, so it's a ring that I will denote by mu star. Well, it's not as trivial as the homology of the point. It's a very big ring. It's a polynomial ring in infinitely many variables in all even degrees. So except for this difference that the cobordism of the point is quite complicated, it has the same formal property of homology theory. Okay. And now one can make all kinds of computation with complex cobordism using, I don't know, Mayer-Vietoris, etc. So for instance, one computes the complex cobordism of the circle, exactly as in homology, is going to be a free module. So here it's a module under the complex cobordism ring of the point, which is complicated for this homology theory. It's a free module generated by, well, the class of a point, and by, if you want, the fundamental class of the circle, the identity. Exactly as for homology, where the homology of the circle is a free Z module generated by the class of the point and the class of the circle itself. And now you can, from this, you can compute the complex cobordism of an abelian variety, because if X is an abelian variety, well, as a topological space, it's going to be a power of the circle. And you can apply a Q-net formula for complex cobordism. And oh, sorry. The dimension, the topological dimension is 2n. So my abelian variety topologically, it's S1 to the 2n. And it is a free module under the complex cobordism ring generated well by very simple classes, classes that I will denote by Fe. They're really the coordinate subtori of this abelian variety for any subset E of one of the set of coordinates. And that's exactly like in homology theory. In homology, the homology of such a torus of S1 to the 2n is generated by as a Z module by the classes of these coordinate subtori. So now I can tell you why this is going to be relevant to the proof. If F is the inclusion of a smooth algebraic subvariety, then I can view F, since Y is a smooth algebraic subvariety, it is a smooth complex manifold. And so I can view this inclusion map as a class in the complex cobordism of X. So I can view the class of F as an element in the complex cobordism of X. And since I have just computed this complex cobordism of X to be a free module with an explicit basis, I can write the class of F in this basis. So let me write it in this way. So F is a combination of the classes of the coordinate subtori with coefficients xe living in the complex cobordism ring of the point. So somehow what I have done here is I have defined, I have associated to Y a cycle class, if you want, not in cohomology, but in complex cobordism. And I claim that this class contains much more information than the usual cycle class map to cohomology. And I will exploit this additional information. Okay. So what I'm going to do next is, if we look at cycle class map to cohomology, classes of algebraic subvarieties, we know that they satisfy that they are not arbitrary, that they satisfy conditions. In particular, they are Hodge classes, which give strong restrictions to cohomology classes of algebraic subvarieties. And here I will do the same. To obtain restrictions on the cohomology class of X, I will exploit Hodge theory. So what I say is that this class in complex cobordism has to be Hodge in some sense. And I will now explain in what sense this class is a Hodge class. So let me first recall the case of cohomology. So if X is a very general Jacobian, so then we know all Hodge classes in cohomology. The group of Hodge classes in degree 2J is generated as a Z module by the minimal cohomology class. Okay. And I will want to consider analogous classes in complex cobordism. And to do so, I notice that the fundamental classes, so of those coordinate subtori of the abelian variety, so they're really the push forward by the inclusion of the coordinate subtori of 1. So they're the fundamental classes of Fe. They form a basis of the cohomology of my abelian variety. So the cohomology, a Z basis, is generated as a Z module by the classes of the coordinate subtori. And using this, I can I deduce that there exists, consequently, there exists a unique class alpha J. So in the complex cobordism group, in the correct degree of my abelian variety, this unique alpha that is a Z-linear combination of my basis elements whose fundamental class the minimal cohomology class. Really, I write, what I'm doing is I'm taking the minimal cohomology class in cohomology. I'm writing it as a Z-linear combination of the coordinate subtori. And I take the same Z-linear combination of the coordinate subtori in complex cobordism. This gives me the class alpha J. And I really think of this alpha J as the Hodge classes as the elements of the complex cobordism of X that are Hodge in some sense. And what I claim then I claim that the class of the inclusion of my subvariety is Hodge in the sense that it is a combination of these preferred classes in the complex cobordism of X. So, okay, so you have to write the indices right. So with coefficients, again, in the complex cobordism ring of the point. So I repeat, this equality should be thought of as reflecting the fact that the class of Y, the subvariety, is in complex cobordism is Hodge. So that F is Hodge in the sense below, that it is a combination of those particular classes alpha who are Hodge in some sense. And so I'm not going to explain the proof. I just want to say that this equality, this reflects the fact that all the cohomology classes obtained by considering Chern classes of Y's and maybe multiplying maybe Chern classes of Y, and then pushing it forward to X is a cohomology class in X that is a Hodge class. So this equality double star, it encapsulates a lot of Hodge theoretic information. It contains the information that all the cohomology classes that I have written, obtained by push forwarding products of Chern classes of Y, they are all Hodge. So it's an efficient way to encapsulate all this Hodge theoretic information. Okay, now I want to extract information from this identity. To extract information I will use numerical invariants that are called characteristic numbers. So characteristic numbers, they're associated with a polynomial in Chern classes. And with a cohomology class. So, and I look at the characteristic number of a class in complex cobordism represented by such a map. And what is the characteristic number? What you do is you evaluate the polynomial P in the Chern classes of M. You cup it with the pullback of your cohomology class. You get a cohomology class in M, and you take its degree. And you get a number. And the reason why it is interesting, it's really an invariant, a cobordism invariant. It depends only on the cobordism class of F. And so I will compute the characteristic number of the class appearing in equality double star associated with an appropriate polynomial in Chern classes. So I will choose it of degree C. And associated with an appropriate cohomology class. And I will choose it to be some other minimal cohomology class. I just make the computation. And so on the left-hand side, what I get is the degree on Y of the polynomial evaluated in the Chern classes of Y multiplied by this minimal cohomology class. And really, on the other side, this is equality double star. On the other side, so you need to make the computation. Many terms vanish, essentially because the coordinate subtori, they have trivial tangent bundle, so their Chern classes vanish. So many, many terms will vanish. And what you obtain, all computations done, is this polynomial evaluated on the complex cobordism class XC, multiplied by theta 2c over 2c factorial. This is the cohomology class of one, the fundamental class of one, the alpha classes. And okay. And this intersection product between cohomology classes on an abelian variety, it's easy to compute as a binomial coefficient. And so here, maybe I should be more clear that what I call P of XC. Yeah. I view the polynomial in Chern classes as a Chern number. So I can view it as a function like that, that takes, say, a smooth projective complex manifold of dimension 2c and associates an integer that is the corresponding polynomial in Chern classes, which lands in the top cohomology of M, and that I can view as a number by taking the degree. Okay, so this identity I call the triple star. And I will want to use this identity, I need to choose the polynomial P in Chern classes, and I will choose it very carefully. So I will want it to satisfy two conditions. The first condition on the polynomial P is that P has the following form. It's a double plus the degree C Segre class. So here is the Segre class defined to be such that the total Segre class is the inverse of the total Chern class. So it's a particular polynomial in Chern classes. And the second condition on P that I will require is that the corresponding Chern number, that is really this function I have considered, which to a smooth projective complex manifold associates these Chern numbers, takes only values that are sufficiently divisible. So more precisely, divisible by this power of 2. And those are the two conditions on the polynomial P that will allow me later in the argument to conclude something. And what I claim, of course, you need to check that there exists such a polynomial P. And I claim that such a P exists if and only if, well, the weird condition on the codimension that appears in the statement of our theorem is satisfied. And this is a non-trivial verification. Proving the proposition requires non-trivial computation. In the complex cobordism ring. Okay. So now what I will do in the last 10 minutes, I will consider the equality triple star. For this particular choice of the polynomial P, and from it I will derive, as I wanted, restrictions on the cohomology class of Y. So let me do it. So to evaluate really this equality triple star in our situation, I need a bit more information that is provided against among other things by the Barth-Lefschetz theorem. So let me tell you what I need. So remember, we have our subvariety Y inside of X, and I will need, let me list the further information that I need. The first additional information that I need is that if I evaluate the sixth Segre class on the variety Y, well, it's okay, by definition, it's the cis Segre class of the tangent bundle of Y. But because the tangent bundle of the ambient variety is trivial, because it is an abelian variety, it is the same as the sixth Schoen class of the Norban bundle of Y. And by the self-intersection formula, it's exactly the cohomology class of Y restricted to Y. The self-intersection of Y is given by the top Schoen class of the normal bundle. This is self-intersection formula. So this is how I'm going to evaluate the top Segre class on Y. Now, okay, this is computed in terms of the cohomology class of Y. And the cohomology class of Y, I know that it is a Hodge class because it is the class of an algebraic subvariety. And I know that all Hodge classes are multiples of the minimal cohomology class. So I can write the class of Y as some multiple of this minimal cohomology class because it is Hodge. And the last information that I need is I will need to evaluate the polynomial Q evaluated on the Schoen classes of Y. And this is a Hodge class on Y. But by some variant of the Lefschetz theorem due to Barth, to the so-called Barth-Lefschetz theorem, this cohomology class comes from a cohomology class on the abelian variety. And it actually comes from, because the restriction map in the appropriate degree is going to be an isomorphism. So it is the restriction of a Hodge class on the abelian variety. And we know Hodge classes on our abelian variety because it's a very general Jacobian. It's again a multiple of the minimal cohomology class. So it has the shape, a multiple of the minimal cohomology class, now restricted to Y. So because it is Hodge, and by Barth-Lefschetz, and we are in the range where the Barth-Lefschetz theorem applies because my ambient variety has high enough dimension. Okay. Okay. And now with all this additional information, I take all of this information and I plug this into my equality triple star. So remember, I had this equality here, and I will evaluate it by taking the polynomial P to be the polynomial I have chosen below. And I just write down for this specific choice of P what I obtain. So, okay, I'm just writing it down. So on the left-hand side, okay, so the right-hand side, I don't change it. I obtain this. And on the left-hand side, so there was this minimal cohomology class. Then there was, I should evaluate P on the Chern classes of Y, but P was chosen to be SC plus 2Q. And so by the above computation, it reads like that. And this would have been this is computing an intersection number of Y, and to compute it in the ambient abelian variety, I need to multiply by the class of Y in the ambient variety. So there is an additional factor coming from the fact that we want to compute the intersection number on Y. So I have to multiply by the cohomology class of Y. Okay. And okay, now those are just intersection numbers on a Jacobian, which are easy to compute. Because we know the cohomology of a principally polarized abelian variety. And only this remains, this very simple equality. And now I'm going to analyze it. Here, this number, by choice of the polynomial P, is divisible, is highly divisible. And really by choice of the polynomial P. This number here, I know it's it's a concrete number. I know it's 2-adic valuation. I know how many factors to divide it. The 2-adic valuation of this number it's exactly alpha of C. It's just computing the 2-adic valuation of a binomial coefficient. And consequently, for the left-hand side to be divisible by 2 to the alpha of C plus 1, it is necessary that this is an even number. And of course, this can happen only if lambda is even. And this is what we wanted to prove, because really lambda was defined to be the integer such that the class of Y is lambda times the minimal cohomology class. That was the definition of lambda. And so this concludes. We have started with an arbitrary subvariety Y, class that is smooth. So classes, I have shown that classes of smooth subvariety are even multiples of the minimal cohomology class. And so in particular, the minimal cohomology class itself cannot be a Z-linear combination of classes of smooth subvarieties. Okay, so really what I think the main information, what I wanted to show in this talk is that okay, to study algebraic cycles, subvarieties of algebraic varieties, it may be useful to use complex cobordism contains information that is topological information that is finer than usual singular cohomology, and it may be sometimes useful to extract information on algebraic cycles. I will stop here.
Thank you very much for the beautiful talk. Do you have any questions? So for the case C equals 3, do you think it's possible to, so by choosing another polynomial P, to study C equals 3, or you think it's already dead end, you need new ideas? And
so I tried a lot to, so for C equals 3, I really think that the method is not going to give anything. It's very weird. It's very much related to, you see, when you apply, for instance, the Hirzebruch-Riemann-Roch theorem to obtain divisibility result on Schur numbers, it depends a lot on how much the Todd class is divisible by 2. Or the coefficients of the denominators, or this kind of thing. And in different codimensions, you're going to look at different Todd classes, and they will have, the denominators, say, will have very different divisibility properties, a bit random. And this is what happens here for C equals 2. For C equals 3, the method fails because the integers that appear naturally, like denominators of Todd classes, they're just very divisible by 2, and it makes this divisibility argument in the end always fail. It's just that some codimensions behave very differently from others, just because the Todd class, the integers that appear, the coefficients of the Todd class are very differently behaved in different degrees. And so for C equals 3, I know the method, I think, fails. And I do not know. So maybe I can even write a question like, are there counterexamples? So to the question of Borel and Effliger. So for on 6 folds for codimension 3 cycles. So I do not know that. So I give counterexamples on 6 folds for codimension 2 cycles, but the case of codimension 3 cycles, I really do not know, because the kind of methods I explained, they really do fail for like these kind of reasons.
And also, do you think the complex cobordism method could also account for the counterexamples for Grassmannians?
Oh, so on Grassmannians, I need to, on Grassmannians, the argument of Hartshorne, Rees, and Thomas is a bit different. Of course, there are no restrictions. Hodge theory is not used at all, because on Grassmannians, all classes are Hodge. So Hodge theory, you will not be able to exploit it on Grassmannians. So their method, as a consequence, is purely topological. What they do is they use Steenrod operations and to detect that some classes are not classes of smooth subvarieties. And I guess you could cast these arguments inside the using complex cobordism, but I think it would only make it more complicated.
I see.
Of
So
course,
it's not
a purely topological argument, you will be able to formulate it using complex cobordism, but it will not be a simplification or.
I see. And then neither more refined.
My opinion is that for our argument, the reason complex cobordism is really useful is that it can encapsulate very efficiently many Hodge theoretic conditions at the same time.
Mm-hmm.
Oh, I mean, and on Grassmannians, of course, there is no.
Yeah, every class is Hodge class, so.
Yeah, and actually, the arguments using Steenrod operations is very short. I mean, you don't want to simplify it; it's already quite simple.
So, are there more questions? Yeah, maybe let me ask one last question. So, which is more about the positive result.
Oh,
so,
yes.
do you think, yeah, at least for abelian variety, would you expect some universal constant, say, or universal multiple m, depending on the dimension of the abelian variety, and such that, yeah, m times the the subgroup generated by algebraic classes is generated by generated by classes of smooth algebraic varieties?
Okay, that is an excellent question. And I am going to ask an easier question that is a bit, okay. Let me ask a question. It is not even known. So is the question of Borel and Effliger. Okay. Does the question of Borel and Effliger for rational coefficients have a positive answer?
Oh.
So in other words, if I look at cycles with rational coefficients, I take an algebraic cohomology class with rational coefficients. Is it a rational combination of classes of smooth subvarieties? It is an open question. The question you were asking is even finer. You were asking, oh, can I control the if the answer to this second question is positive, then all algebraic cohomology classes have a multiple that is a combination of smooth subvarieties, and you're asking, oh, can I control this multiple? But we don't even know that it exists. Of course, this is probably the most important question in this circle of ideas. With rational coefficients, even on Grassmannians, we do not know that this question has a positive answer.
Yeah, very, very interesting question, this one. So are there more questions? So if there's no more question, then let's thank Olivier again. Yeah, thank you very much.
Well, thank you.
Yeah, so this is the end of today's AGEA seminar. So the next section will be in 2 weeks. So same time, also 2 speakers. So in 2 weeks, maybe this will be the last AGEA seminar. So please, yeah, if you want to attend for the last time, so please, yeah, please show up. Yeah. Yeah, so thanks again for the 2 speakers today, Jae-hoon and Olivier. And yeah, so see you next time. Bye bye.